Welcome, everyone. Thank you for coming. It's a pleasure to host Brian Metzger, who's a professor at Columbia University and also has a joint appointment at the Flatiron Institute. Brian is perhaps, I don't need to say this in this crowd, but he's perhaps most well known for coining the term kilonova, but he's also worked on a variety of really exciting topics related to supernova, compact object mergers, and nucleosynthesis, and I think that's what he's going to. Thank you. So, Brian, take it away, please.
Thanks, Caitlin. It's a pleasure to be here. My first time really visiting the Arizona, so it's been a great experience away from the snowy Northeast, although it hasn't been that snowy this winter. So yeah, today I'm going to talk about the origin of the some of the heaviest elements in our universe. You probably have heard quite a bit about the kilonova event we saw 5 or 6 years ago from GWST 0817. I want to give you my own, take on that event, but I also want to make the broader point that it's probably not the only source in nature where we can produce these heavy elements. And I'm going to key in on the birth of black holes in other environments. And I'm going to try to argue that much as we have some evidence now that heavy element formation is associated with short gamma ray bursts, they may also be associated with the birth of black holes and longer duration gamma ray bursts. And I want to highlight the contributions from my mainly postdoc and student collaborators, particularly Jennifer Barnes and Daniel Siegel on this work. Okay, and I encourage you to stop me if you have any questions. Okay, so one of the goals of nuclear astrophysics is to identify when and where in our universe the heavy elements were created. We know the lightest elements were forged in the Big Bang at the beginning of our universe. The intermediate mass elements were largely formed in stars and expelled into space when those stars die as supernova or in their stellar winds. But as we get to the bottom of the periodic table, those elements heavier than iron, about half of them, their origin remains obscure. Nevertheless, this includes the precious metals like gold, silver, and platinum, and the transuranic elements, the so-called rapid neutron capture R process elements. Their origin, we've known about the nuclear physics of the R process since the 1950s, but their astrophysical origin has remained under debate. And it's actually an old problem. It's not so easy to form these heavy nuclei. Even if you could get a star hot enough, you have this prohibitive Coulomb barrier to overcome in order to forge a heavier element through standard thermonuclear fusion. So in principle, it's easy to turn an ordinary element like isotope of iron into one of gold. You just take an iron nucleus and you bombard it at a very high rate with neutrons. And in this way, if you bombard it faster than it can beta decay back to a stable element, you can form a heavy isotope that will ultimately decay back to a gold isotope. But then the question shifts, where in nature do I find this really high abundance of neutrons that I'm able to bombard an iron nucleus at a very high rate? I need a very high abundance of neutrons because they decay away into protons in 10 minutes. And as you can believe, most ideas discussing this involve neutron stars because they're obviously reservoirs of neutrons. And an obvious way to get those neutrons out into space where they can do something is to collide those two stars together. And I'm sure you're all aware that this is what LIGO detected on August 17th of 2017, detected its first binary neutron star merger. This is just showing you the chirp signal of this event. Remarkably, the total mass of this binary was about 2.7 times the mass of our sun. This is remarkably similar to the galactic binary neutron stars that we know will merge within a Hubble time. And so it's fairly reasonable to expect that this type of merger is common in our own galaxy. And if it did produce heavy elements, would be seeding some of the stars that eventually form the sun. I think you're also all aware of the electromagnetic follow-up campaign that accompanied this event, but I'll just briefly recount it based on this movie. So the first thing that happened is there was a burst of gamma rays detected by the Fermi satellite and the integral satellite, which localized the burst to this part of the sky. It took LIGO a few hours to get its gravitational wave error region together, but when it did so, one of them overlapped the error region identified by Fermi. Virgo, the Italian gravitational wave observatory, further localized it to this 30 square degrees, and there were several groups using different techniques that looked at all of the galaxies within this error region and detected the fading counterpart in NGC 4993, which was remarkably close. We didn't expect the first merger to be so close, 40 megaparsecs. And in fact, I think we now appreciate, based on ongoing studies from LIGO, that this is probably a once-in-a-decade event that occurs this close in our own backyard. And so what did we detect? Really detected this fading blue, initially blue, and then becoming very red counterpart, discovered independently by several groups, first by Coulter et al. And this was very exciting. It was like unlike anything we had seen before. We see supernova all the time, but they aren't this bright. They don't fade this rapidly, excuse me, they are this bright. And in terms of its color evolution, it was quite unique. And of course, we had been thinking a lot about how these events should appear, and this looked remarkably similar to what we would expect from the production of a significant quantity of these heavy elements in the merger that as the matter expands into space, this radioactive heating from the material keeps it hot, causes it to glow, and that's how we're able to see this event. And I'll talk a little bit more about this if you're interested. So this is just showing the sort of multicolor data that was taken over the first 30 days or so. As you can see, it evolved very quickly in the ultraviolet bands, was more persistent in the near infrared. And there's been a lot of effort since this paper to try to model this emission and what it tells us about the composition of the material ejected from this merger. We can probe the total quantity of the material. Essentially, we know the rate of radioactive energy input, and so we know the luminosity, so we know how much material is required to produce the luminosity. And then also, by looking at the colors of the emission, we can learn something about the specific composition of this material and the velocity of the material. And so what was learned from this event was that there were likely at least two components of mass ejection from this event. One, which was a little bit lighter, a few hundredths of a solar mass expanding with a very high velocity, which was responsible for powering the early blue emission. And this material was relatively devoid of the heavier R process elements. I think I have a slide on this in a second. But the bulk of the material, maybe twice or three times as much, was expanding with a significantly lower velocity, about a tenth the speed of light. And we think that these sort of persistently red colors are indicative of this material also containing some of the heaviest R process elements. Again, I'll talk about this in 1 second, but the main point is that by modeling this, we can infer something about how much material was ejected, something vague about its composition. There were individual spectral features identified in the event, a claim of a strontium line, although I've recently heard it might also be a helium line. And there were some potential emission features claimed based on late time Spitzer observation. I'm not going to talk too much about that.
Sorry, Brian.
Yeah, go ahead.
A lot of data points with error bars on the plot. What are they from?
These are from a whole variety of different telescopes. Yeah, so each one of these is a particular band measured by a particular optical or infrared telescope. Sorry. So yeah, these are the near infrared bands, and then these are, yeah. Okay. Sorry, I don't have all of the references. There's a huge number of references that go into this. I probably should have put them all up here. So okay, anyways, well, how do we actually? I just want to go through a little bit of the physics of what the colors are telling us about the composition of the material that was produced. Basically, the colors of the kilonova reveal something to us about the ejecta composition. So if you just have the lighter R process elements, the opacity is not that much different than in a supernova, where most of the opacity comes from iron. So there are a lot of lines. I mean, most of the opacity in the ejecta is coming from a forest of Doppler broadened lines in the expanding material. And when you just have the lighter R process elements, most of the atoms' valence shells are the D shell electrons. There's a lot of these lines, but not a huge number of them. So they have a relatively low optical UV opacity. And so if you just had exclusively light R process elements, you would get a pretty rapidly evolving event. It becomes transparent quickly, and it becomes transparent early when the ejecta is hotter. So you get something that is fast, blue, and hot. On the other hand, it was shown by Dan Kaysen and Jennifer Barnes that if you have some of these heavier elements, those at the bottom of the periodic table, the lanthanide and actinide elements, their valence structure is in the F shell. And so in a sort of combinatorial way, the atoms have many more line transitions, which completely blanket the UV and block out any UV or optical light. And so the emission is not able to escape the ejecta until a little bit later when it's cooler. And so the emission tends to be slower evolving and redder, with a peak actually in the near infrared band. Let's see, so basically when we saw both of these components, the early blue part and the later red part, it's really telling us something, that there were sort of different components of material, probably geometrically arranged slightly differently. We have reasons to think that the lighter component may be ejected along the polar direction of the explosion. And one thing I want to emphasize right now is that whether or not we get lighter R-process nuclei or these heavier ones at the bottom here, in turn is telling us something about how neutron rich the ejecta is, because the way we're forming these elements, remember, we're starting with a lighter element and bombarding it with neutrons at a high rate. If we have fewer neutrons, we sort of run out of neutrons and only form these lighter R-process elements. And so fewer neutrons, we get something blue. If we have more neutrons, we can capture our way up to these heavier elements and we get something red. So we can also infer from this event that the material ejected was exposed to different quantities of neutrons, had different neutron richness to it. And if I were giving a talk, I would go into a lot of this in more depth if it was just on the mergers, but I want to get to the main point of my talk. But what I want to address, the important question is, what produced this ejecta? What physical process during the merger produced this few hundredths of a solar mass expanding across a range of velocities with a range of different compositions? And we're still debating this, but I'm going to show you a numerical relativity simulation of two merging neutron stars. This is by Radice and collaborators. You're seeing the final few stages, the final few orbits. This is all happening within a few milliseconds. As the two stars get close together, they begin to tidally distort each other. You get some matter ejected out of the outer Lagrange point of the binary, which comes out in the equatorial plane. Then the two stars collide together. They produce an oscillating remnant, which is shocking and driving material in all directions. And then at the end, you have some matter that has so much angular momentum it remains in a rotationally supported disk around the central object, which in this case succumbs to gravity and collapses into a black hole right there. So there are different sources. Oops. Still going. I guess it doesn't want to stop the simulation. So there are different sources of ejecta from the merger as a function of time after the coalescence. There's the matter that comes out very quickly, promptly, dynamically during the simulation at the merger itself. This is what, if you see a numerical relativity simulation, this is mostly what they're quantifying. This includes, as I mentioned, tidal material or material from the shocked remnant. This material tends to come out very quickly with a high velocity, up to 3/10 the speed of light, typically. And the quantity depends on the mass ratio of the binary and the equation of state of the binary, et cetera. But there isn't generally a whole lot of this. It's typically of order 1,000th of a solar mass to at most 100th of a solar mass. The more important source in terms of total mass ejection actually occurs later from the accretion disk that forms around the newly formed black hole, the one that we think over the ensuing seconds accretes onto the black hole and powers the gamma ray burst jet. It turns out, as I'll talk about in a second, that these black holes are fussy eaters. So if you put 1/10 of a solar mass disk around them, not that entire matter makes it into the black hole, you'll typically get a disk outflow which contains a few hundredths of a solar mass. And this material tends to come out over a longer period of time, of seconds or so, with a lower speed, it turns out. So the thing I want to emphasize is that this dynamical ejecta, which is what most numerical relativity simulations study, is probably not sufficient to explain the kilonova that we saw in 170817. So this is showing you on this axis the mean ejecta speed and the total ejecta mass for a range of simulations. These are a bit dated, but so people have filled out this graph more, but it hasn't changed the qualitative picture. And then over here are sort of where we need in terms of mass and velocity to explain the blue light R process and heavier red kilonova from 170817. And what you see is that basically the simulations are all up here. No matter what we do in terms of mass ratio or equation of state, we generally don't produce enough material. We can maybe produce some of what's called the blue kilonova, the fast expanding low velocity material, although it doesn't have the right composition usually. But we can't really explain the bulk of the material that we inferred for modeling the kilonova, which has a lower speed and is quite a bit more mass. And so I think it's it's unlikely that the dynamical ejecta alone can explain the ejecta we saw from the merger, but we can explain it fairly naturally is this post-merger accretion disk I mentioned. So this is a general relativistic MHD simulation, now a few years old, showing the accretion of this torus onto the newly formed black hole. You're feeding the black hole at an incredibly high rate, like a solar mass per second or something, so it cannot cool by photons. Photons are completely trapped in the accretion flow. What's driving accretion is the magnetorotational instability. What does cool the disk are neutrinos. So the midplane of the disk could get to temperatures of several MeV. And so the midplane where it's hot can cool efficiently through neutrinos. But the upper layers of the disk where it's cooler can't cool through neutrinos. So you have turbulence in the disk driven by the MRI, which as it dissipates in the upper layers, there's nothing offsetting the cooling. And so it drives a thermally driven outflow. Even if you don't have a very large scale magnetic field, you drive an outflow from these disks. And we find that only about 70% of the torus mass makes it onto the black hole. The remaining 30% is ejected in this outflow. And since a typical torus mass is around 1/10 of a solar mass, you can easily get a few hundredths of a solar mass ejected this way. And the speed that you measure from the simulations is indeed about 1/10 the speed of light, which is what we inferred for the bulk of the kilonova from 170817. So you can produce the quantity and velocity of what we observed. So what happens in these disk outflows is the midplane is sufficiently hot that you've broken down everything into free neutrons and protons. But as matter goes out of the disk, that ratio of neutrons to protons can change depending on the absorption of neutrinos or antineutrinos that are being emitted by the disk. But as you get further out, and the people are still working on improving the radiation transport of the neutrinos to more accurately determine this composition, most people agree it's neutron rich, these outflows. How neutron rich is somewhat up to debate. As the matter goes out, the free neutrons and protons combine, all the protons combine with some of the neutrons to form alpha particles. Those alpha particles quickly form heavier seed nuclei like iron, and then you bombard those seed nuclei with neutrons, and that's the way that you create an R process. And this is all happening within a second or so after these nuclei leave the midplane of the disk. So if you have enough neutrons and you eject the material, it inevitably will form these heavy nuclei. This is just showing you an R process reaction network. If you want to see this in detail, here we're following a single one of these fluid elements out of the disk as it decompresses from high densities and temperatures. This is proton number, neutron number, and so you initially form these seed nuclei. I'm not showing you the seed nuclei formation stage. These are the seed nuclei. And then as you capture neutrons, they move to the right. And then as they beta decay, they move up to the left. And in this way, capturing and decaying, you can, as the fluid element decompresses, you can move up to form a wide variety of different heavy elements from the single fluid element. And then you run out of neutrons about 1 second, and then everything decays back to the stable valley over the course of minutes and hours and days and weeks. And it's the accumulation of all this radioactive heating from all of these decays that is powering the kilonova that we saw.
Can I ask?
Yeah.
So maybe you're going to get to this, but what is the compositional difference between your ejected and your disk? Is that entirely moderated by how many neutrinos are interacted with?
Good question. So yeah, in the midplane of these disks, and I'll come back to this, tends to be very neutron rich. So in terms of the electron fraction, it's 0.1, so it's like a neutron to proton ratio of 20 or so. But that, as the matter flows out, it does tend to convert some of those neutrons back to protons. But you still have more neutrons than protons.
Well, but there's no intrinsic difference, is there, between two regions, or is there?
Between the two regions.
The stuff you say is ejected quickly versus what stays in the disk for a little bit.
There's no initial difference, but in the disk, the weak interactions can change the composition. That's going to be an important part of the story, actually, because I'm going to argue it didn't actually matter that the disk was made of neutron star material. It will turn out that these disks become neutron rich on their own, independent of what they're made out of. So yeah, I'll get back to that. So there is the dynamical ejecta was raw neutron star guts, if you will, but the disk material it actually would have been neutron rich even if it hadn't formed from a neutron star. So what you could do is you can take the final abundance pattern, you can add up all of your fluid trajectories. This is what many groups do. And then they do a nice thing where they plot and they compare it to the solar system R process or to their famous metal poor star R process abundance pattern. And depending on if it fits or not, they claim victory. But as I mentioned, this is all very uncertain because it depends on this radiation transport of the neutrinos, depends on a lot of nuclear physics off the valley of stability we don't understand. But I think it's broadly true that these disk outflows can be sufficiently neutron rich to produce the abundance patterns we see. So then the question is, are mergers enough, if you will, to explain all of the elements on Earth? And so you can estimate this pretty easily. Before the formation of the sun, at what rate you need to form R process elements in the galaxy per year. You just count up all the R process elements, divide by the age of the galaxy, you get about 10 to the minus 6 solar masses produced per year. We now know from LIGO roughly, although it's still uncertain at the 2 order of magnitude level, the rate of neutron star mergers in the universe, which you can translate into a per Milky Way rate. And then you can ask the question, how much R process would each merger need to produce given these rates to explain the abundances on Earth? And that number varies between a few thousandths of a solar mass and a few tenths of a solar mass. And what we inferred for the kilonova from 1797 is about in the geometric middle of this. So in other words, within the uncertainties, yes, the mergers could produce all of the R process on Earth, but we can't say for sure that they definitely do, and it could be as, so it's basically, we can't tell if it's 10% or 99% until we have more events, until we nail down the merger rate better. And I think there are some natural challenges to mergers being the only source of galactic R process, which have actually in some sense been known for many, many years in some cases. One of these is the discovery that the ultra-faint dwarf galaxy Reticulum-2 is highly enriched in R process elements. Most ultra-faint dwarfs haven't been so fortunate to experience even one R process pollution event in their lives, but this one Reticulum-2 had some enormous R process pollution event early in its chemical evolution history. But the escape speed from that galaxy is less than 10 kilometers per second. So in order for a neutron star merger to have polluted that galaxy, it would have to have remained bound to the galaxy despite the 2 supernovae that blew up the binary, that blew up the 2 stars that form the neutron stars. It would have to get an extremely tiny kick. And then it would have to merge promptly enough in order to generate the very early generation of stars in that galaxy. Impossible? No. Maybe you might question if it's the most natural thing. There are lots of chemical evolution, evolutionary model constraints on the R process, some which may favor or disfavor mergers. I'm going to point out one that was very striking to me. If you just look at the ratio of europium over iron as a function of iron over hydrogen of stars in the galactic neighborhood of the sun, what you see is that this ratio is generally dropping. Ignore the colored lines, that's a model, but just it's just these points and the blue points is generally dropping as you go forward in metallicity. Most of the iron at high metallicity is coming from type 1a supernova. And so what this is saying, the fact that this is dropping is saying that most of the europium was formed in our galaxy, or suggests was formed before most of the iron. Okay. So whatever's making the europium is happening earlier in chemical evolution history than 1a supernova. Whereas whereas it takes a while often for 2 neutron stars to actually merge, much like it takes a while for type 1a supernova to happen after star formation. So this is suggestive that maybe there was a fair bit of europium formed very promptly in the galaxy. These are not ironclad. I'm just trying to introduce some doubt into your mind whether mergers are the most natural source for all the R process. Okay, so I think everybody knows that there are 2 classes, I'm switching topics a little bit. There are 2 classes of gamma ray bursts, which are separated by the hardness of the bursts, but mainly by their duration. We have the short gamma ray bursts, which typically last less than a second, and the long gamma ray bursts, which typically last about a minute. And we now have pretty good evidence from 170817 and other constraints that binary neutron star mergers are the origin of most short gamma ray bursts. And we also have pretty good evidence that most long gamma ray bursts originate from the core collapse of massive rotating stars, things I'll refer to as collapsars. So in this case, we saw a kilonova after a short GRB. In this case, we actually see exploding stars appear after some long gamma ray bursts, although not all of them. And so if you wanted, if you just look at a snippet of a GRB, it's actually really hard to tell whether you're seeing a short GRB or a snippet of a long GRB in terms of the prompt emission properties. They're remarkably similar. There are some differences, but so if you wanted to attribute both to accretion onto a newly formed black hole, what you'd say is that binary neutron star merger is what you get when, or sorry, short GRB is what you get when you feed a black hole a tenth of a solar mass over a second after a neutron star merger. And a long GRB is what you get if you feed a black hole a few solar masses over, say, 30 seconds. Okay. These typically have roughly 30 times the gamma ray fluence of those. So the jet power, if you will, integrated over time is about 30 times higher for these, which is why they're 30 times longer. They have similar luminosity. So I think it's natural to say, okay, these can produce in our process, and most of it's coming from the black hole accretion disk, as I argued, that maybe we should seriously consider whether collapsars could also produce our process in their disk outflows. So this is how a collapsar works. In cartoon form, you have a massive star. It evolves a helium core, which then evolves to the point, onion skin structure to the point of core collapse. Let's say it's typically a 10 solar mass helium core. If the star is sufficiently rapidly rotating, when it collapses, the inner regions maybe fall in, and if the star doesn't explode, form a black hole. But the outer layers, because the star is rotating, they have enough angular momentum that they land in an accretion disk around the black hole. Some of that material makes it into the black hole, power the jet, and some of it may be ejected in a disk wind, similar to happens after a merger. So you could take these types of models. I could take, Alex Hager or Stan Woosley's model, or somebody's model, which tells me the angular momentum and radial structure of the star, and I can, calculate at what rate different layers of the star fall into the black hole in a very simple way. You just sort of calculate the free fall time and then calculate how long it would take to go through a disk. And so you can plot the black hole accretion rate, if this is in solar masses per second, logarithmic, versus accreted mass. So this is like a time axis going this way as you accrete the whole star. And then this is showing you sort of the timeline of how a collapsar works. So within the first few seconds, you accrete the first few solar masses. There will be a proto-neutron star phase. It's quite possible, because the star is rapidly spinning, that the neutron star itself will be very rapidly spinning. It may be a so-called magnetar. It may try to blow up the star. There's something we call an MHD-powered supernova. It may or may not completely succeed, in the sense that that neutron star may continue to accrete mass and eventually form a black hole. But nevertheless, it could be that there is a powerful explosion. Once you do form a black hole, then you can start producing a relativistic jet, which doesn't take particularly long to break out of the star, maybe a few seconds. And then once it's broken out of the star, then the GRB jet comes out, and you can see gamma rays, presumably for the next minute or so. And during this phase, the accretion rate onto the black hole is quite high. It's between, a solar mass per second, maybe down to a thousandth of a solar mass per second. So what we wanted to study was whether these accretion flows that are feeding the black holes in collapsars can produce heavy elements. So we didn't have the type of costly simulations that we would need to study the entire global problem of the whole star falling in, creating a disk, magnetorotational instability. There are groups, Northwestern group is actually starting to do this now. What we did is we said, okay, let's just set up a disk that is representative of 3 different epochs in the collapsar evolution. One, when the accretion rate's a tenth of a solar mass per second, 100th of a solar mass per second, and 1,000th of a solar mass per second. And then we basically did the exact same calculation I showed you earlier for the case of a neutron star merger. We let it accrete onto the black hole. We tracked what material fell into the horizon, what was ejected in winds. We followed the nucleosynthesis of that outflowing material. And what we found is that for the 2 highest accretion rates, 10th and 100th of a solar mass per second, that the disk, even though, as I'll talk about in a second, did not start neutron rich, the disk quickly becomes neutron rich. And the outflows from the disk retain that neutron richness and are able to produce an arc process, both for these 2 highest accretion rate cases. This is showing you a plot of the electron fraction, which is the ratio of protons to total baryons in the disk. And you see in this high accretion rate case, the electron fraction in the mid plane is around 5%, and it's around 10% here, which is sufficiently neutron rich for an arc process. And we found that if we trace the outflowing fluid elements, that for the 2 high accretion rate cases, we were able to produce up to the heaviest arc process elements. The third case, we didn't, the accretion rate wasn't high enough to neutronize. I'll talk about this in a second. So we instead produced quite a bit of nickel 56. So should be a bit of a mystery to you. How did we go from a star, which is not neutron rich, all the onion skin structure of a star, they're all alpha elements with equal numbers of neutrons and protons. I'm feeding them into a black hole. So how did I get a very neutron-rich accretion disk near the horizon and outflows? Well, this has actually been known for 20 years that these outflows from GRBs self-neutronize. The disk is so hot that there is a very quickly an equilibrium established between these two weak interactions. You have electrons, you're hot enough, you have electrons and positrons forming from gamma-gamma pairs like in the Big Bang. And the electrons capture on protons making neutrons and the positrons capture on neutrons making protons. And these two reactions are in balance. But it turns out that if the disk is sufficiently dense that the electrons are degenerate, it turns out that you suppress positron formation because to create a positron, you have to create an electron, but the Fermi state is full. So this reaction wins and it drives you to be neutron rich. This is just showing a diagram from Bella-Baroda of density and temperature showing contours of this equilibrium electron fraction. And GRB disks tend to lie up here, a very neutron rich composition. And you can show analytically in a few lines that this constraint on the density you need to become electron degenerate and to cool by neutrinos to become dense and to enter this neutron-rich equilibrium, you could show that that's a lower limit on the accretion rate onto the black hole, which you can express in terms of the viscosity of the disk and the mass of the black hole. And so independent of what you're feeding the black hole, if you're above this accretion rate within the inner few RG, you're going to become neutron-rich, and I would argue likely produce neutron-rich outflows.
Can I ask another question?
Yes.
Pardon me if I'm missing, at least what, a long time ago I learned happens in the core collapse, but so you have your iron core, but I thought the classic thing is as you collapse is when that becomes neutronized itself, that long before you make the black hole, that you have a neutron-rich stuff that's going into that happened, I would think would happen before you made the black hole, not after that.
Yeah, so it's true that you form, the core is becoming neutron rich right at the point of core collapse.
I mean, the whole thing goes, that's how you make
And then you form the neutron star where the neutrinos are trapped and it is star deleptonizing, becoming a neutron star. Yeah, but that whole neutron star, that whole proto-neutron star ends up in the black hole. So because that would, so we're feeding matter from layers that are a bit outside that have not yet.
So it all just disappears.
Yeah, that material, the proto-neutron star, the assumption is that ends up in the black hole. Now, if the black hole didn't form and you had a neutron star in the center, then you still have this accretion disk around the neutron star, but you'd have to worry about the neutrinos from that neutron star possibly changing these compositions. But yeah. Most of that material ends up in the black hole. Yeah. Okay, so we have a critical accretion rate, and you could see that it's around 10 to the minus 3 solar masses per second for a typical alpha found by MRI simulations. And that was why. So this basically is consistent with what we found with Siegel. The two high cases where we're above this threshold neutronized and produced our process, and below it we didn't. We still got hot enough to make nickel 56, but not enough to neutronize. Okay, so then, so then you can ask the question, well, can collapsars really compete with mergers as important sources of the galactic arc process? And I think if you just do the back of the envelope calculation, it suggests they could. The argument goes something like follows. A typical GRB, short GRB jet is around 10 to the 49 ergs of energy, maybe 10 to the 50. A typical long GRB, when you correct for beaming, is around 10 to the 51 ergs. This is a factor of 30 difference. So if we know that in a short GRB, we typically accrete a 10th of the solar mass, which is about the size of the disk that numerical relativity simulations show. And we saw that event produced a few hundredths of the solar mass in 170817. Then if I just scale it up and say, okay, the long GRBs are more energetic because the black hole accretes more, then they should also, for every gram into the black hole, if there's a gram out in this arc process, you could get maybe 10 times as much material. Now, the rates of short and long GRBs in the local universe, the rate of short GRBs is a bit higher than long GRBs. But actually, as you go to higher redshift, that's not obviously true. But anyways, even if you just take the local rates and you say, what is the contribution of collapsars versus mergers? You just take kind of this estimate of their yield per event times the rate, and you take the ratio, you get a number that's of order unity. So this suggests that you should consider long GRBs seriously if they are being powered by black holes, and if the accreted mass is commensurate with how energetic the GRBs, which are assumptions. And I would argue furthermore that, as I already talked about, there are hints in the early universe that are challenging to understand in terms of mergers, like the our process in dwarf galaxies, whereas the collapsars are literally observed to occur in low metallicity dwarf galaxies, which in some sense are the building blocks of the Milky Way halo. And so this very old image from Andy Fruchter showing the host galaxies of long GRBs and showing that there are these typically high star formation rate, irregular low mass galaxies, which you could argue it's not a perfect, Alex G corrected me on this, it's not a perfect thing to compare it to reticulum-2 in our own galaxy, because this formed at much higher redshift than long GRBs. But you get the point that in some sense, these are the building blocks of the halo, are dwarf galaxies, not too terribly different from where we observe collapsars. So you know, if there are our process going on in these galaxies and then they get swallowed by other galaxies, those galaxies will have our process. So okay, yeah, go ahead. So
you mentioned that for the case of binary neutron star mergers, there is a problem of escape velocity.
yes,
Where the velocity of the ejecta seems to be much larger than the escape velocity of these dwarf
not of the ejecta. The argument is that the binary that forms has to stay bound. So the neutron star binary, there has to be two supernovas to form both neutron stars. And that binary has to get a kick which is smaller than 10 kilometers per second. If it gets a larger the kick than that, it will go out of the galaxy and merge out here where there's no gas around, and then it won't pollute that next generation of stars. Now, if Svi Paran was here, he would say, oh, we know there are some neutron star binaries that get tiny kicks. But the argument is precisely how tiny. Yeah.
Can you capture a neutron star, like by coincidence, or are
There
we
were
talking
some
about-
groups that looked at that idea that you shoot a neutron star binary. I think it would require very fine tuning to shoot it and have it merge in a different dwarf galaxy, I guess. So okay. So what I want to talk about now is how to test this idea, since I've speculated a lot. So the idea is that we want to be looking maybe for our process signatures in GRB supernova. As I mentioned, after a sizable fraction of long GRBs, if you wait for the afterglow to fade, you see the emergence of a supernova. We see that these are associated with supernova in some cases. So what we have here is we have an explosion, which again, it may have been blown up by the neutron star before it collapsed to a black hole, or maybe the jet itself blew up the star. So you have a lot of ordinary stellar material that has exploded, but in the center you have this black hole which has been accreting and ejecting our process material. So you have a kind of a kilonova core, a neutron-rich core of material surrounded by ordinary supernova ejecta. These are stripped envelope supernovas, so free of hydrogen. So in some sense, you have a kilonova inside the supernova. And so at early times of the supernova, you just see the ordinary material. But then as time goes on, you just see deeper and deeper. And at some point, you might be able to start to see the signatures of these process elements. And so I worked on this with Jennifer Barnes. We just created a kind of toy model where one of the free parameters of the model is how much our process is produced in the supernova. And the other free parameter is how far out I mix it in mass, because these accretion disk winds will presumably interact with the exploding star, and there'll be some mixing, and it may move out towards the surface, or it may stay embedded in the core. So we leave that mixing coordinate as a free parameter. And I'm not showing you the full light curve. I'm just showing you the R minus K colors, which you could think of like redness of the supernova as a function of time in days. And so if we embed all of the R process in the core, then we don't really see any strong deviations from the ordinary supernova color evolution. But as we mix the R process further and further out, we should start to see significant reddening, maybe around 50 to 100 days after the explosion. This is just a typical model. So naively, we thought, okay, the search strategy would be, okay, let's follow up GRB supernova on time scale of months, see if they're suddenly becoming redder, and then maybe to confirm we get a Webb spectra or something like that. And so there have been a few attempts to do this. I was tangentially involved with this. This is a student at Caltech working with Mamsie Kastelwall, where she read about our model and said, okay, I want to test this. So she collected a bunch of supernova from the literature, archival supernova. These are broadline type 1c supernova. So not all of these have GRB, but they are the type of high kinetic energy explosions, which are in some cases associated with GRBs and probably require a central engine beyond a normal neutron star. And so here I'm showing, she also got some follow-up observations of newer ZTF events. And so here I'm showing the R minus J color from her work as a function of time after the peak of the event. It's quite a busy plot. Most of these are the data. And the purple lines are a bunch of these earlier models, like I mentioned from Barnes here. But we vary the amount of our processed mass and it's how far it's mixed out of the ejecta. And what you see is that most of the events sort of are getting redder, and then they sort of come back down here. There's not too many that are consistent with these extremal R process pollution events. There is one event, 2007 I, which does get very red, but some people speculate that might be dust formation. It may be an interacting supernova that formed dust, which is a terrible contaminant for this type of search. So I would say that we don't have any evidence from this. We did, the comparison of the models with and without our process and got kind of, equally good or equally bad fits depending on your interpretation. So I would say, her interpretation was that we don't really see the type of near infrared excess that we predicted if we produced a tenth of a solar mass and mixed it to the fairly far out in the ejecta. I will say though that I think there's still, many of these events are still very sparsely sampled, and only a few of these actually were accompanied by GRBs, and these weren't the classical powerful GRBs. These were low luminosity GRBs, which may not have as powerful of an accreting black hole. There's some reason the jet is less powerful or the central engine is less powerful. And unfortunately, our models are still hindered by the fact that we don't totally know what to assume for the colors of the R process material. There's been some theoretical work by Kenta Hotakazaka looking at the nebular emission from these R process lines, which is what you asymptote to at late times when you have this sort of R process core. There's a lot of uncertainty with that, but I would say we don't have any evidence yet, but I think this is going to be the first, and I hope other follow-up observations. I was quite excited when this GRB went off in October, the brightest GRB of all time, 21009, 221009A. This was a highly anomalous GRB in terms of its brightness. This was a plot I took from Todd Thompson right soon after the event, where he plotted the fluence of Fermi gamma ray bursts, and they kind of follows a log normal type distribution. But this event had a fluence that was like orders of magnitude higher than any previous event. I think in the interim there was one other event here, but it was sort of a 6 sigma outlier in the population, which people have suggested this may be a once in 1,000-year event. It produced these nice X-ray rings it was going through our galactic plane and produced these off dust in the galactic plane. So it's one of the closest GRBs ever, redshift 0.15, had one of the highest isotropic energies ever. So that combination, very close, very high intrinsic energy, made it this extremely bright event. And also it had a number of very high energy photons detected by the LASSO collaboration. But anyways, for me, it was very exciting. It's like, okay, great, a long GRB in our backyard. We can wait until the supernova appears and we can get an infrared spectra and see if there are any R process lines. And in fact, there was a TOO approved with JWST. I was a little bit involved with this. It was taken 13 days after the explosion. Unfortunately, we would have liked to test this model. You would have liked to wait until the ejecta had become transparent, but in 13 days, if there is a supernova, it's probably still rising to peak. We're not nearly past the phase where we could really peer into the ejecta. And furthermore, the afterglow was still much brighter than the supernova. So what we got with our observation, while exciting the first Webb spectra of a GRB, once corrected for extinction, turned out to be basically an uninterrupted power law. If there had been a supernova of the brightness of 1998 BW, we might have expected to see some excess here. What we were looking for were a number of lines. There are a number of lines from the usual suspects, iron, cobalt, et cetera, in the ejecta, which have been seen in, for instance, 1A supernova spectra. But we were looking for a number of R process lines predicted by Kenta. And unfortunately, we have a featureless spectra. If there was our process, we're too early. So it went into sun constraint. I'm under the impression that new observations are possible in April. I don't think 6 months is too late. Let's look again, hopefully, and maybe we will see some of these lines. I'm doing for time. Okay. All right. There was another event you may have heard about. This was a so-called long GRB with a kilonova. This was GRB 211211A. This was an interesting event because it was technically a long duration gamma ray burst. This is the gamma ray light curve. So depending on whether you're talking about Fermi or Swift, I think it lasted between 30 and 50 seconds. So definitely in the long burst category in terms of its duration. But in terms of its other properties, offset from the host galaxy, some aspects of the prompt emission, it actually looked a lot more like a short gamma ray burst. And what was particularly odd is when you subtracted away the afterglow, which is the non-thermal part from the GRB jet hitting the ISM, there was an excess emission, particularly in the near-infrared bands, which was remarkably similar to what was observed from 170817, as I mentioned earlier. So it looked like, and there was no supernova detected, so you could rule out a bright optical supernova, I don't remember, 100 times, 1,000 times fainter than 1998 BW. So this appeared to be a long GRB with a kilonova. And this led to a lot of speculation. Of course, we had just with Jennifer Barnes worked on collapsar models to see, with our process. So the question was, could this emission that we saw, the kilonova, in fact, be an R process enriched collapsar? So we did apply our model to try to fit the infrared and optical data for this event, and wrote this paper up. And what we found was that we could get a fit, and you could see it here to the different multi-band data. But the properties of the ejecta from this collapsar had to be very merger-like. So we needed less than a solar mass of ejecta from this collapsar, quite a high velocity, and a small amount of our process, and just a tiny bit of nickel 56 produced in order to explain the data. So it could be a collapsar, but it would be a highly atypical one compared to what we usually see, where we usually see several solar masses or 10 solar masses. Here we would need less than a solar mass. Most of the star would have to fall into the black hole with just a tiny bit of material ejecta. So I think it's sort of a matter of Occam's razor, which you would prefer. Either you need a long GRB with a highly atypical collapsar following it, or you need to accept that a merger that made a kilonova can also make a long GRB. Now it's a bit difficult to understand why there should be gamma ray emission for 50 seconds after a merger of two neutron stars. It's conceivable that the two neutron stars could merge and form some kind of magnetar that doesn't want to form a black hole right away and is spinning down for 50 seconds and producing this emission or something. But it's unfortunate that LIGO was not on, because this source was at a distance where it probably could have told us if it was a merger, is my understanding. It was at 300 megaparsecs, but if they know when and where to look, they have sensitivity. So they could have told us if this was a merger or not. Fortunately, they weren't on. It would be great to know. So I don't know what to favor. Either it's a weird collapsar or a weird merger. Okay. time. I want to talk about something completely different, black holes and the parent stability mass gap. Okay, so you probably know single stars should not form black holes between 50 and 120 solar masses because their cores evolve to the point where they become unstable to collapse and thermonuclear explosion. So there should be no single black holes in this mass range. Yet LIGO observed a merger of two black holes, each of around 80 solar masses. Okay, so the question is, how did you form these black holes in the mass gap? And there are a number of ideas that have been proposed. Maybe you merge black holes in succession in a dense nuclear a stellar environment, like a galactic nucleus or globular cluster. So they're actually second generation black holes that had already merged. Maybe you have a black hole in an AGN disk that accretes a bunch of gas. Maybe you merge two stars at an opportune time and you are able to somehow fill this gap, although that's a little difficult to do. I want to propose an alternative, which is let's start above the mass gap, because if you have a sufficiently massive helium core, it will form a black hole. It's above 120, and let's excavate some mass. So the idea is something I'll call a super-collapsar. This is the speculative part of the talk, where I have a 150 solar mass star, for example. It collapses in, forms a black hole, but not 150 solar masses makes it into the black hole. A significant fraction is ejected in the same sort of disk outflows that I've been arguing this whole talk. So we did actually explore what this signature of this, the electromagnetic signature of these super-collapsars are. And so, we found that if you start off with this 150 solar mass black hole, endowed it with a rotation profile similar to those of lower mass collapsars, and just figured out what would go into the black hole, what would get ejected, you could eject, say, 50 solar masses of material, of which maybe up to 10 solar masses could be, or 20 solar masses could be our process material. So like 100 times more prodigious than a merger. And in the end, leave 100 solar mass black hole. So you can't hide these events because you're ejecting radioactive material. So we calculated what the signature of these things would be. And basically, they're just like sort of a kilonova on steroids. It's rather than lasting a day, it's like an infrared transient that lasts for several months and is very bright in the near infrared with very broad lines. So these are fairly distinctive features if we could discover these very rare events. And what we did is we took the formation rate of these that would be needed to explain the single event by LIGO and folded it through whether these could be detected blindly by future surveys like Rubin or Roman. And we found it's going to be hard for Rubin for all of our models to detect many of them, even over the course of several years. We did find that one of the planned surveys on the Roman Space Telescope had a decent chance to detect one of these blindly. So looking forward to that, I think probably the more promising thing would be to see one of these emerge out of a very energetic GRB, because these could produce very energetic GRBs. So when we turn back to the boat, my hope is that maybe we'll see the tail end of one of these so-called super kilonova. Okay.
Is the limiting factor on Rubin just that it's mostly optical and these are mostly emitting?
Yeah, that's the thing. Yeah. So what we've assumed here, which is quite conservative, is we've assumed that these 150 solar mass stars, the binding energy in the core is like 10 to the 53 ergs. So we've assumed that they can explode and that everything falls into the black hole except for the disk outflows, which is why we get this pure infrared. If we had an explosion, then we could get some optical with ordinary material. We could get some optical emission. And I wouldn't be surprised if there is some brief optical emission here in reality, which means we could detect them with LSST, but we would have to follow them up in the infrared. Okay, and basically finished. So to summarize, I hope I'm pretty confident that most of the ejected from 17917 is too massive and too slow to come from dynamical inflow, but it is consistent with coming from the outflows from the black hole accretion disk, one that powered the GRB jet. Similar accretion flows qualitatively should form from the collapse of massive rotating stars. They are the model for long gamma bursts, which are otherwise pretty similar to short gamma bursts, except they produce 30 times the energy over 30 times the duration. Despite very different initial conditions. One, you're feeding a neutron star guts. The other one, you're feeding stellar material with equal numbers of neutrons and protons. They try to argue that collapsars can produce neutron-rich outflows because weak interactions in this very dense accretion flow necessary to produce the high jet power is drive it neutron-rich. And order of magnitude estimates suggest that the contributions could be comparable between mergers and collapsars. And I think collapsars ease some of the tensions as you look in the early chemical evolution history of the galaxy. I'm not saying mergers aren't, in fact, mergers may still be the most important source. It's just that if you go back early in the chemical evolution history, I think that having some collapsars as well helps. And the way to test this is with late time infrared observations of GRB supernova. We don't have any convincing evidence so far, in part because we don't understand ordinary supernova very well. I would argue things like dust formation are going to be a major contaminant for these searches. But I think we have a possibility with the boat. And we did have this event that might have been a collapsar. If you take these 10 solar mass ordinary collapsars and you scale them up by order of magnitude, you could conceivably produce a progenitor for LIGO's black holes. Not merge hierarchically, just start with a more massive black hole. And don't let all of it fall into the black hole. I start with a more massive star. But this comes with a prediction. If you're going to excavate mass from a star, it has to be ejected into space, which means it should produce an observable transient, which may be detectable by future observatories. And with that, I will finish. Thanks.